So for the nitrogen cycle on the global scale, we have a basic idea of some of the pools and some of the fluxes. And now we're going to cover the anthropogenic changes in the nitrogen cycle at the global scale. In the past century, human activities have approximately doubled the quantity of nitrogen fixed from the atmosphere into terrestrial ecosystems. When we looked at those numbers as far as the fluxes are concerned, the Haber process, that industrial fixation of nitrogen, is the number one anthropogenic process. It's the primary way that new nitrogen is entering ecosystems through anthropogenic means. This is figure 14.9, and it shows anthropogenic fixation of nitrogen over time. And these are the different sources. So we have legume crops, for example. When we plant soybeans, they're going to fix a lot of nitrogen. We have fossil fuel nitrogen. So when we burn when we burn fossil fuels, there's going to be some production of nitrogen oxides. And we've got nitrogen fertilizer through the Haber process. Now the range of estimates for natural nitrogen fixation are somewhere between 100 and 150 teragrams of nitrogen per year. And if you add up these 1, 2, 3 sources, we quickly get to that same level. So when we say that humans have doubled the amount of nitrogen that enters into ecosystems, it's through these three factors: legume crops, fossil fuel burning, and nitrogen fertilizer. So again, this is figure 14.8. It shows major pools and fluxes. In industrial nitrogen fixation, we added 100 teragrams. In biological nitrogen fixation, kind of the natural nitrogen fixation, this is the upper end of the estimates at almost 150 teragrams. So if you take fossil fuels at 25, industrial nitrogen fixation, and then biological nitrogen fixation, which here includes both the natural and crops, you can see that it's really the Haber process that is the predominant single source, and then the biological nitrogen fixation, if you add up the two, is even more. All of these gains that we get from additional fixation are balanced to a certain degree by patterns of denitrification and gaseous nitrogen loss associated with animals. And that's really led to an increase in the amount of nitrogen that we see, reactive nitrogen, in the atmosphere. N2O, nitrous oxide, NH3, and different oxides of nitrogen. If we take a look at the third panel of figure 14.7, we had already looked at how CO2 concentrations have changed, how methane concentrations have changed, and here's N2O concentrations over the past 1,000 years. And again, these are sampled from ice cores in Antarctica. N2O concentrations have been relatively low, somewhere in the order of 260, 270 parts per billion. And since then, since the Industrial Revolution, we saw a large increase. And that's especially due to the increase in the use of the Haber-Bosch process, the Haber nitrogen, so industrial nitrogen fixation, as well as changes in fossil fuel burning that we've seen an increase in, as well as the planting of legumes on a global scale. And so just like that inflection point being in the late 1800s, we're seeing an inflection also in N2O concentrations and an increase in the amount of reactive nitrogen in the atmosphere. Now, earlier we had compared the global warming potential of CO2 to methane, and now we'll compare it to nitrous oxide. And whereas we had, for methane, somewhere on the order of 23 times the global warming potential of CO2, nitrous oxide is 200 times. So small increases in nitrous oxide concentrations in the atmosphere lead to large increases in the warming potential of the atmosphere. Here's figure 2.18 again, and here's the warming potential of CO2, and here is methane. And you can see that the amount of radiative forcing associated with N2O increases is similar in magnitude to methane. And it's less than methane, but it's still significant. And so those increases in the N2O concentrations, although the absolute concentration is low, because of the really high warming potential of N2O, increase the radiative forcing in the warming of the atmosphere. So while 20% of the warming was associated with methane, we're talking somewhere on the order of 6% of the warming that's occurred could be associated with increases in N2O concentrations. In total, we've doubled the N2O flux, so somewhere on the order of twice as much N2O is being emitted from terrestrial ecosystems as before. The sources of this N2O, a lot of that is from feedlots, so places where you're going to have high nitrogen availability, and places where we're going to concentrate relatively low C to N materials and have a lot of high nitrogen availability. Feedlots is one of them. Ammonia flux has also tripled, and so not only are we getting a lot more N2O into the atmosphere, there's a lot more ammonia too. And there's a number of sources for ammonia, but domestic animal waste is another one. And so places when we have large manure piles or slurries, these are areas where you're going to get a lot of release of ammonia into the atmosphere. Now, ammonia in the atmosphere is not important for warming. It doesn't absorb infrared radiation, but it's biologically active, especially in precipitation. So ammonia that enters into the atmosphere, it's going to come down with precipitation, and that's an increase in nitrogen supply. For oxides of nitrogen, somewhere on the order of 6 to 7 times increase in the rate of NOx flux into the atmosphere. And that's associated in large part with an increase in nitrification. So greater amounts of nitrogen being available in soils leads to greater NOx formation. But also combustion of fuels. And when we have fossil fuels that have nitrogen in them, they're going to react with oxygen to give us different oxides of nitrogen. And so there's different situations where under high temperatures, the combustion of fuels in cars, for example, and in power plants leads to the production of NOx, which again is a reactive form of nitrogen when it comes down into terrestrial ecosystems. So those are some of the major changes that have happened to the nitrogen cycle on a global scale. In general, there's been an increase in nitrogen availability globally due to a number of these changes.